Today we're going to talk about reaction rates and catalysts. So to begin with, the speed of the reaction can depend upon two main things. First one being concentration of the reactants, and the second one being temperature of the reactants. So I want you to picture something real quick for me. If you have two cups, one has really cold water in it, and one of them has really hot water in it. If you drop in a little bit of food coloring, which one do you think is going to change color the quickest? The cold water or the hot water? And why? You can even go get a glass of water if you want to and give it a try. But what you'd realize and what you'd find out is that the hot water would cause that molecules to disperse a lot quicker. Why is that? Well, it's something called diffusion. Diffusion is just simply the ability of a substance to travel without an electric field force, or for instance a fan that pushes it along. It's simply going to go from an area of high concentration to an area of low concentration. And so that's kind of how concentration helps into it. But the other thing is with temperature, if you have a lot of energy in your system, those molecules are moving a lot faster, right? Because as we learned previously, the more energetic something has, the more motion it's going to have. And that correlates directly with heat, with temperature. And so what's going to happen is if you have a reaction, it's going to move a lot similarly to these food dyes. If you have a high concentration area, it's going to move to a low concentration area. It's going to diffuse out. And the more energy it has, the quicker it's going to be able to do that. And so that speed of a reaction is called the reaction rate. Because with our example, we just simply have one product that's dispersing. But let's say that food dye needed to react with something in the mixture. Then you'd have to deal with, okay, how much of reactant A, which might be your food dye, do you have? How much of reactant B do you have? Because if you only have, say, one molecule of the thing that the food dye wants to interact with, it's got to search all the way throughout that solution in order to find that one molecule. And so how fast it can react depends upon how quickly it can find the other component of the reaction in order to react. So whenever you're talking about the speed of a reaction, you're talking about how quickly can reactants become products, and that's your reaction rate. Alright, so why do those two matter? Well, for one, reactants have to come in contact in order to react. And so what you see in this picture right here is you've got two reactants, and if they come together and they collide, then they could rearrange and create a product. And so that's what happens when you've got nitrogen and oxygen coming together. They can form nitrogen monoxide. The more easy that this reaction can take place, the quicker it will take place. The more interactions, the higher the energy, the faster the rate. So the more interactions you have, that can be because you have a higher concentration, or it can be because the individual molecules or atoms have a higher energy. And so if either of those two are true, then you'll have a faster overall rate. So then there's still a little bit of a barrier. So let's think about this. How fast you run a mile could be dependent on a couple things. It could be based on, oh, I feel really good today, I feel really slow today, or it could also be based on the fact that it's a mile straight uphill. Or if it's a mile straight downhill, you're going to run that a lot faster. Activation energy is kind of like that. It's the other remaining component. Because if you have a whole lot of energy, you're going to run it fast. But if you have the same amount of energy and you're running uphill versus you're running downhill, the reaction is going to be slower. Okay, so activation energy is what describes the energy barrier that must be overcome in order for the reaction to take place. So the faster the molecule is moving, the more energy is present. And also, the more energy it's going to be able to have in order to overcome that barrier. So basically, every single reaction has its own unique activation energy. And it's kind of just the way of quantifying how much energy you have to have in order for it to proceed. A catalyst then is directly related to that activation energy. A catalyst is used in order to speed up a reaction by lowering the activation energy, by taking that hill, that minimum amount of energy that you need in order for a reaction to take place, and making it smaller. Wouldn't that be great if we had a way in real life just simply to lower our barriers and make it a lot easier to succeed? That's what a catalyst does for molecules, for atoms, in order to produce a reaction. What's true about it is a catalyst is never used up. Instead, whatever form it goes into the reaction, it exits the reaction in the same form. And so what's awesome about catalysts is if they serve one reaction and force that reaction to speed up quicker, it can go on and do an immediately catalyze another reaction. And so it can be used over and over again, and it can make all these reactions speed up. So my last question on here I have is, how is a catalyst different from a chemical reactant? Well, chemical reactants, you start with something and you produce something else. Reactants, if they're present at the beginning of the reaction and at the end, they're not a reactant because they didn't react. A catalyst is the exact same from the beginning to the end. Reactants are not. They are going to change form. So here's the answer here, just kind of in written form. A chemical reaction, by contrast, is consumed during a reaction as it is transformed into a chemical product. So let's look at an example of how a catalyst works. So here's that same example where nitrogen and oxygen are coming together. Well, what if they have to meet and collide in that exact same orientation where the two ends are close together? If you can see in this box right here, they're coming in the wrong orientation because the red one needed to be oriented in that same kind of shape in order for the two ends to interact with each other. But in this case, they're coming in the wrong direction. Why would they do that? Random motion of molecules. As your molecules are moving around, they're going to orient all kinds of reactions. So what happens in this situation, if they come in the wrong direction, they're just simply going to bounce off and keep on going. If they come in this correct orientation, then they're going to collide, they're going to react. What we need to look at is what does a catalyst do? Well, what a catalyst can actually do is it forces these two reactants to come in the correct orientation. So by doing it, it makes it so instead of having maybe 50% of the molecules that collide react, you might have 100% of them that come in and collide react. Why? Just simply by controlling the order at which they come in. So it's sort of like a ball glove. How it forms around that ball, it catches the ball and holds it in place. The catalyst does the same thing. It catches maybe both the nitrogen and the oxygen, holds them in place so that they can, or forms their orientation appropriately so that they have time to react before they move on. So all different catalysts will do different components, but the idea is somehow they're able to speed up the reaction by making it so that there's an increased number of collisions. So this is an example here. Chlorofluorocarbons, they act as catalysts that can destroy ozone in the stratosphere. So the idea here is if we have depletion of stratospheric ozone, that's what's going to lead to the ozone hole. And so the idea here is if you have too much chlorine in your atmosphere, you're going to slowly be depleting the ozone. And so if you notice here, we have chlorine on the left side of the equation, and we also have it on the right side of the equation, which means chlorine was not produced by anything, so it's not a product. And also, it's not a reactant. Why? Because it's present at the end, so it was not consumed. So that means since it's present at the beginning and at the end, it has to be considered the catalyst of the reaction. Everything else can either be categorized as reactants or products. So here's kind of an example that shows you the activation energy. So remember that energy barrier we talked about previously? It takes it for ozone and makes it much lower. So now ozone does not need as much energy in order to form diatomic oxygen. Instead, it just needs a much lower amount. So that means that the reaction rate is going to be sped up with the increase of chlorine, which is the catalyst, which is what you see right here. And so how you see it above the arrow, that's how you denote that the catalyst is present. You just write the name of the catalyst above the arrow. So how do the catalyst speed up a reaction? These 2 points right here. Well, they're not consumed, and they lower the overall activation energy. How? By increasing the number of collisions. So here's an example that kind of showed scientifically that chlorine was one of the reasons, or was in fact a catalyst for this reaction. If you notice on the bottom in blue, chlorine monoxide, as it increased, what happened to ozone? It decreased. So they show this direct relationship between the two. A bunch of other studies, but we're able to prove that chlorine was in fact a catalyst for this ozone depletion. So now, mostly catalysts are not bad. For the most part, they're very good. They're used biologically, they're used physically, they're used mechanically. In this example here, your catalytic converter is part of your car. They used to be made entirely out of platinum, so that's why catalytic converters were being stolen from cars for a while, because the platinum is a very valuable metal, and so they were getting stolen. But what it would do, it would convert dangerous pollutants from exhaust to less toxic substances. And so it was able to make all of these dangerous pollutants that are present in your exhaust and make them react and collide and be converted into new substances that it could then release into the atmosphere. Nowadays, if you don't have a platinum catalytic converter, once they started getting stolen a lot, they switched over, and instead of having platinum do both the reduction and the oxidation, which we'll talk about later in our next exams content. But now you have two different metals that can do the same purpose that platinum did, palladium and rubidium. Okay, so with those two items, those two elements, they're able to do the same kind of thing. The idea that you're converting from a dangerous substance to a more atmospherically friendly one. Alright, so I want you to think about this question for a second. An internal combustion engine works by drawing a mixture of air and gasoline vapors into a chamber. The action of a piston then compresses these gases into a smaller volume prior to ignition by the spark of a spark plug. So why do you think the engine even bothers squeezing all these vapors into a smaller volume? What's the point? Why would you want to do it? Would gasoline not ignite in the larger volume? Think about it for a sec. Okay, it would. It would still ignite, right? But the smaller volume increases their concentration, and it therefore increases the number of collisions between all the different molecules. So as you're increasing collisions, what happens to your reaction speed? It's increasing. So you're increasing the number of reactants. So, kind of recap, reaction rate depends on concentration and temperature. Activation energy is the minimum amount of energy required for a reaction to occur. A catalyst lowers the activation energy by increasing the number of collisions of the reactants. And catalysts are not produced by reactions, neither are they consumed.